On the right here is the block diagram for the network controller. This section here is the I2C core where you control it through these different registers. The prescale register, which controls the clock generator, command register, which tells it when to send or receive and other commands, status register tells the current status of the I2C line, like if it received the data or if it got an ACK or a NAC. Transmit register is your transmit buffer, and receive register is your receive buffer. And this white box here is the game network logic that is implemented here, where we have the master core instantiation shown here with the state machine variables shown here, where there's different states for this networking logic, where there's a reset state, status state, configuring the prescaler, start stop state, load the address state, load data state, idle, right, and acknowledge interrupt. So current progress with the I2C is that we descoped it from our current game, since I couldn't get it working with the slave module. The slave wouldn't recognize the valid I2C transmission between the two due to some kind of glitch in the signal where the start condition gets messed up. So the plan for I2C was descoped.
This is our attempts to use UART to communicate between boards. For example, this is player 1, so I'm going to show the ship moving forward, and then I'm going to end its turn. As you can see that its turn has ended here by the turn LED turning off. And on the other board, its turn LED has turned on, which means that it's its turn. For once, the ship has moved correctly. However, when we attempt to replicate the effort of moving the ship forward and firing on it, you can see that the logic remains internally consistent on this board. However, on the opposing board, the ship moved to the incorrect location and the health didn't update. But I have detected it's my turn, so I can move forward and then fire on the ship. Again, you see it internally consistent, but on the other hand, the changes did not propagate to the other board. So our game logic works. However, whatever we're sending across is not working correctly. And so this is why we decided to try another track for communicating between boards.
So for our last resort, we resorted to using a direct data bus connection between the two FPGA boards. We basically pass all the needed signals that we need between the two boards through the wires onto the breadboard and back through wires to the other board. This didn't really work as we intended. We do get the correct signals being passed through the wires in the direct bus. However, with this added logic, we are unable to receive user inputs now. So the game wouldn't work without the user input. So this plan had to be rescoped also.
In our game, this is a state machine of its high-level decisions. At the beginning, it starts at a reset state, and then it'll first try to fire on something. If it can succeed at that, it'll then try to move, and then if it can move, then it will end its turn. If it cannot fire on something, it'll try to move first, but if it cannot move, it'll give up on moving and try to fire again. Either way, once it has gone through both fire and move states at least once, and has either moved, fired, or given up on that action, it will then continue on to end its turn. This is achieved using state machines. As a high-level state machine, there are 3 states for the AI: a reset state at the beginning, a wait state wherein it waits for its turn, and a calc state in which it will calculate its turn and then output the appropriate information. Within the calculation state are several substates representing the fire and movement. The state machine here represents the calculation state, where it has 4 main sections: fire, move, update, and done. Fire is determining whether I can fire. Movement update is when it will update the rest of the game with its decision, and done means it's the end of the turn. And then there's also a movement submachine, where there is also a movement submachine state. There's also a movement state machine in which to determine how to move, it has a start state where it determines where it needs to move, a pathfinder state where it actually determines the correct path, and then a completion state where it will then update. In particular, the AI has several rules for firing and moving. For firing, it decides to shoot the weakest ship, and if there's only one weakest ship, then it will fire on it. If not, it will use a random number generator to determine which ship it will fire on. This is achieved using a target vector, which represents whether or not a ship can be fired on based on visibility, health, and whether or not it's in range. This is achieved using several submodules. And then it goes through a case statement and then use a random number generator for the rest of it. For movement, it's a little more complicated because of pathfinding. It will first try to retreat weak ships. If not, it'll try to send a healthy middle strength ship toward the center of the board. And if not that, it will check to see if there's any powerful ships in the back and then send those toward the middle rank. And if all of those conditions are fulfilled, then it will be satisfied with its board position and not move anything. This is achieved using the move module described before, where it uses if statements to check each one of those conditions, as depicted here. And then once it figures out where it wants to move, it goes through the pathfinder. In this particular case, the pathfinder determines which in the 8 cardinal directions is the place it wants to go relative to where the ship already is. And then using the random number generator, it will then choose a random spot along that cardinal direction for it to go. So that if I'm trying to move to the top left of the ship, it will randomly generate a number, and then choose based on that. If the space is empty, it will then move toward it. Unfortunately, because of limitations on our project, we were unable to implement the AI because it takes up too much logic slices on the board. and then it would not fit with the rest of our logic. So we prioritized having PvP versus P versus AI in this particular case.